Hello, everybody. My name is Nick McKee, and today I'm going to be discussing with you guys the key components and concepts of high performance liquid chromatography, or better known as HPLC. To get started with HPLC, I'm first going to discuss with you guys the types of samples that are analyzed with HPLC. It's important to note that usually larger, more complex samples are used with HPLC, and the reason why is because with GC analysis or gas chromatography analysis, the samples are heated up to change the phase from liquid to gas. And sometimes with those larger, more complex molecules that have sensitive R groups or sensitive bonds to heat, it's really hard to analyze those samples because it can hurt the GC instrument or change the composition of the sample as a whole. So HPLC is really advantageous in that respect that there's no heat involved and you can analyze those samples easily. Something that's cool about HPLC is that you can use things called vial inserts, and what it does is it makes it so that uh, the amount of sample used, it doesn't have to be a large amount of sample. So if you're using a sample that's on a microliter scale and you don't want to dilute it up to zero point 0.5 milliliters, you can still analyze those small samples since the sample vials make it much easier for the injection needle to grab that amount of sample. So that's really cool in that respect with regards to samples. A key principle related with HPLC is the idea of using gradient elution. And basically, the premise of it is that it uses multiple solvents to control um, the amount of components running through your column at any point. So basically, it's changing the relative polarity of the mobile phase in the system. So let's say you have an analyte in your column, and let's say you're running water as your solvent, and most of your components of your sample have already flown through, and you're trying to get your analyte to go through. Well, depending on whether the analyte is more polar or non-polar, you can change the solvent to be more polar or non-polar to uh, make the analyte flow through faster through the column. So basically, you can selectively make things flow through the column faster based on changing the relative polarity of the solvent going through. Now, something to keep in mind with this is that you need to make sure that the solvents are miscible with each other. So you don't want something like oil and water going through the column because it can form globules that can clog up the column, and that can be no good because it can obviously make your sample unreadable or make it look different or just hurt the column in general. So you need to make sure that those solvents are miscible with each other. And on the HPLC itself, you can see on the bottom right, there's a red square around 4 solvent bottles on the top. That's typically what the solvent system looks like in the HPLC. So that's pretty cool. In order to get the whatever you're trying to analyze through the column itself, the column is very densely packed with the stationary phase. And if you were trying to run the sample through the column, it would take forever for it to get through the column, or it might not even run at all. So we use pressure to push the solvent and sample through the column in a timely manner. Usually at any point, there's about 300 to 400 bar of pressure pushing the solvent through the column, and this is done by the use of a pump. And as you can see on the bottom right, there's a picture of the HPLC again. That little section right there, that's devoted to the pump itself, and you can change how the the amount of pressure output from the pump at any point by using the interface that it has. So that is the pump and how pressure works within the HPLC. All right, so now I'm going to be discussing the stationary phase with you guys. So before I do that, I'm going to discuss what's on the outside of the column. So the column itself is about 5 to 25 centimeters long, and you can see different variations in column length on the bottom right. They're made out of stainless steel, and the reason why is because there's a large input of pressure being pushed through it at all times. And to prevent any breakages from happening, they're made out of stainless steel so that it doesn't bend or break due to the pressure. You can use these things called guard column protectors to keep any contaminants from hurting your column at any point. So Basically, you screw them on at the beginning of the column, and it'll catch anything that's not your analyte or solvent running through, and it can potentially save you thousands of dollars in replacing columns. Um, so now that you know how the column is structured on the outside, I'm going to discuss the stationary phase. And basically, that is what's packed on the inside of the column. It's your adsorbent. And as you can see on the top right, that is kind of a depiction of the most commonly used column, which is a packed column. And those yellow dot looking things represent the beads that are inside of the column. And those beads have different compounds attached based on what stationary phase you want. So the most common type of stationary phase used is a C18 column. And basically, those beads have long carbon chains, specifically 18 carbons long, attached to those beads. If you were wanting to change the polarity of the stationary phase, all you'd have to do is find a column that has a different type of chain attached or a different compound attached to sift through your analyte. So for this example, as I just said earlier, the C18 column has 18 carbon chains. You could find one that has different lengths of chains, ones that have different substituents on it, whatever you think would favor the polarity that you are looking for in the column, that's what you could find. So you basically just changing whatever compound is attached to those beads that changes the polarity of your stationary phase. So now that your sample has completely separated into its components, you want to be able to detect them as they pass through the HPLC. And the way we do that is we use an instrument called a UV vis spectrometer. And what this does is it emits a certain wavelength of light within the UV vis spectrum, and it'll see a compound that absorbs that amount of light and will make note of it. So we can use that to our advantage because we can selectively and non-selectively see what materials are passing through the HPLC once they've been separated. How you do this, you choose a specific wavelength that matches both the analytes you want and the solvent that you're just running through. You want to make sure that they're not different wavelengths, and you want to make sure that the wavelength is the same for both. If you don't, you might not see one or the other, or maybe peaks will look the same or they'll be hidden, and that can be one disadvantage of using a UV vis. But if you're able to find a way where the peaks are both separated and they both absorb at the same wavelength, then that works great. And that the advantage is that we can specifically target specific analytes and see when they come off. So once your components are all separated and completely through the HPLC, there's sometimes where we really want to know what those components are based on maybe their molecular weight. And a way we can do that is by using a mass spec. And similar to a GC-MS, what we can do is attach a mass spectrometer after the HPLC, and it'll catch those components as they come off the HPLC, and it'll analyze them and give you their molecular weight at specific times. So you know exactly what components what they were separated into and how they were separated. In our case at the University of Tulsa, we use two mass spectrometers. The first one kind of acts like a mass filter, so it gives you that initial reading of the components as they come off, and the second one analyzes those components as they're fragmented from their parent ions. And how that happens is through the use of different ionization methods. So when your components are analyzed through the second mass spectrometer, they're fragmented from their parent ions. And what you can do is to kind of do a reverse analysis and piece together those components to figure out what possible parent ions there were as they came out of the HPLC. And we can use different ionization methods to do that. Typically, we use electrospray ionization in HPLC. So it's a very soft method so that when your components come off from the HPLC, whenever they split into their components, they don't fragment right away as they come off the HPLC. You can analyze them through the mass spec, and then uh, those will be fragmented from there. Whereas in GC, usually they're fragmented as they go straight into the mass spec from the GC. Another ionization method that is used within HPLC is atmospheric pressure chemical ionization, or APCI, and that is another way to another ionization method typically used in HPLC. In GC analysis, this isn't really used in HPLC since it'll fragment your parent ions before they even hit the mass spec, but it's electron impact ionization, and it's typically used in GC. So in regards to the mass spec machines themselves, they are very difficult to maintain, and the systems themselves are extremely expensive. Just the system's turbo molecular pumps that require replacements frequently, they're about $10,000 a piece. So you can imagine what the whole machine as a whole can cost. So it requires a lot of money, but they're really helpful in research since they can analyze compounds extremely usefully and specifically. So that is everything on mass spec and HPLC. I hope you guys enjoyed, and I will see you all in the future.